Okay, moving into the second half here of Chapter 11, Section 1, we're going to get into the formulas here for the areas of three new quadrilaterals here. The first of which we're going to talk about is going to be trapezoids. Now, if you recall from an earlier chapter, a trapezoid is a quadrilateral that's got only one pair of parallel sides. So in this figure that I've drawn at the bottom, it's this side and this side here that are going to be parallel, but this side over here on the left and this side over here on the right are not. So that's our kind of understanding of what a trapezoid is, and a little bit more with vocabulary now. The two parallel sides are called the bases of your trapezoid, and it doesn't matter which one is which, but I'll call this one base 1 and this one down here base 2. Those two bases have to be different lengths. If they ended up being congruent, then this trapezoid actually becomes a parallelogram instead. And then, again, the height of your trapezoid is going to be defined as the perpendicular distance between those two bases. So there should be a right angle symbol right over here, and then this piece in the middle of that, notice it's a dotted auxiliary line. That's the height of your trapezoid. And if we go way back to that slide we covered at the beginning of this section here, guys, it is still true. Boy, I'm putting a lot of circles and boxes around this, but it's really, really important. Base and height must be perpendicular. That was true in a parallelogram. It was true when we got to triangles here, and once again, now that we are in trapezoids, base and height have to be perpendicular to each other. So it might not be a bad idea just to write that little statement there, how about with an exclamation point too, over and over and over again. So with all that established here, the formula for area of a trapezoid is more complicated than the formula for either area of a parallelogram or a triangle. It's going to be 1/2 times the height of that trapezoid times the sum of its two bases. And notice the bases are added together in parentheses, meaning that that needs to be done first. So that's the formula for it. If you care that much about where that formula comes from, you'll notice that what I did over here, guys, is I cloned that original trapezoid that I had here. These two figures should be identical. Yeah, and I think they are. And if I spun this one 180 degrees and made it look like that, and then put it right next to the original trapezoid, we'd get a big new shape that looks like this. And if I were to kind of highlight that in yellow, you'll notice that what we are dealing with right here is a big, long parallelogram. And we already know how to find the area of a parallelogram. Let's think about that. This quantity from here to here is identical to the piece from here to here. That means that that's B1. So if I were to figure out the base of this entire figure, it would be the sum of base 1 plus base 2. So that gets you the base of this entire parallelogram, and h is the height. So area of the parallelogram would be the sum of base 1 plus base 2 multiplied by h, which is its height. So that would give us the area of this entire parallelogram here that we have in yellow. But that's not really what we wanted here, guys. We wanted to get rid of this piece. Let me move that out to the side a little bit and erase. So what are we now interested in? Only half of that original parallelogram. So if we wanted the area of the trapezoid, we would simply take a 1/2 times this formula that we had right here. Now I'm going to move the h to the front, and then base 1 plus base 2, and that's where the formula for area of a trapezoid comes from. Basically, if you doubled your trapezoid, you would have a parallelogram, but we only want half of that. Okay, so that is the third formula that we need to know here from this section. Let's see it in action now. All right, taking a look at this figure right here, we've got a quadrilateral. Ooh, I remembered to put arrows in this one. Go me. So the top and the bottom here are parallel to each other. All right, and we've got a 10 and a 14-inch side, top and bottom. The left and right sides, both on a diagonal there, are 7 and 8. And then, of course, there's that red 6-inch side in the middle there. Once again, you're looking for right angles here. Because, let's write this over and over again, guys, base has to be perpendicular to height, and that's what we've got right here. So, step number 1, let's write our formula here. Area of a trapezoid is going to equal 1/2 times our height times the sum of our two bases put together in parentheses. Step 2, let's fill in what we know. We're looking for the area, so I leave that as A. And we've got now a 1/2 multiplied by the height of this figure, and the perpendicular, or the right angle right there tells me that 6 is going to be the height. Now again, I'm going to put units here because I want to make a point. 6 inches. And then in parentheses, base 1 and base 2. Those are the two parallel sides, and it doesn't matter which one goes first or second because we're just adding them together. So 10 inches plus 14 inches. That's the sum of our two bases. And step 3, let's go ahead and, in this case, we're not really solving an equation, but we're evaluating the right side. Probably going to do two things at once here, guys. I'm going to go ahead and multiply 1/2 times 6, and then at the same time in parentheses, I'm going to add those two things together. But I should say that's because I'm doing this by hand. If you guys wanted, you could take this entire expression right here and put it all into your calculator in one step, and it'll give you the answer. So for me, 1/2 of 6 inches is going to end up giving us 3 inches. And then in parentheses, 10 inches plus 14 inches is going to be 24. And when you're adding units together, inches plus inches, that still gives you inches. So now it's a multiplication problem. 3 times 24 is going to be 72, and inches multiplied by inches are going to give us square inches. So that's our answer here for this example. The area of that trapezoid is going to be 72 square inches. So as the formulas start to get more complicated, I'm hoping you guys understand what I mean when I talk about a 3-step method and why it's really useful for helping you to stay organized right here. Step 1, write out the original formula. Step 2, fill in what you know. And then step 3, evaluate or solve depending on what kind of problem it is. Okay. Speaking of which, here's the second, and I think this is the last trapezoid problem we're going to do. And in this one here, guys, again, this is a little bit different. The area has been given to us, and we're being asked to solve for n, which is this missing side over here on the right side of the figure. But I do see two parallel sides here, so that means we're dealing with a trapezoid, and they've given us the area, so I know that this requires the formula, once again, for area of a trapezoid. So step 1, write out your formula. Area equals 1/2 times your height, and then base 1 plus base 2 in parentheses. Step 2, fill in what you know. Now, this is a unique problem here. We've only done one like this. That was in the previous video on 11.1, where we were given the area. So 1200 goes here on the left. Guys, that's why it's so important that you include the left side of your equation every time you write a formula. A lot of people, when I say, hey, what's the formula? They just want to give me this, the right side, but I really want you guys to focus on the idea that a formula is an equation, and that means it has to have a left side, then an equal side, and then a right side. So we got to make sure we have all of that. Otherwise, we're kind of stuck on a problem like this. So 1200 equals, okay, 1/2. And do we know the height of this figure? Well, I think I see the height. I've got the right angle right here, and that's going to be an h. I wasn't given that amount right there, so it's going to be really tempting for me just to put an h right there, but you're going to see why that's a problem in a second. In parentheses, I need the sum of the two bases. The bases in a trapezoid are not necessarily the bottom and the top, although that's the way most of us like to think about it, and we kind of saw that here and in this problem as well. But the bases, let's remember, are the parallel sides. So the parallel sides are going to be this side of the figure here on the left, which is 10 and 50 put together. That's going to make 60 for one of the bases. The other base, though, is the other parallel side, and that's going to be n right here. Now, everything I've written down on this line is correct, but we've got a big problem, guys. We are being asked to solve for n. So it's okay that I don't know the value of that number right there. I'll leave that as n, but this h is a problem. You can't solve an equation that has two unknowns. So what that tells me is, and this is the way you guys want to approach some of these harder problems now, we must be able to solve for h. So I got to go back and erase the h that I put there, and we're going to need to put a constant value in here and figure that out. So how are we going to work on that? Well, I think we're going to focus on the idea that we have ourselves a right triangle here in yellow. We know it's a right triangle because of that 90-degree angle right there. And two of the three sides in that right triangle were given to us. So we can always solve for the third side in a right triangle either by using the Pythagorean theorem or by Pythagorean triples. And you guys know me, I like triples. So if I were to just rewrite that triangle right there, all right, and I had a 10 here and a 26 and this was an h, I would look for a common factor that I can divide out from 10 and 26, and that's a 2. Dividing that out, that's a 5 right here, a 13 right here, and now I recognize this as a 5, 12, 13 right triangle where everything is being doubled. So I'd put the 12 right there inside the triangle and then multiply out. 2 times 12 means that h has to be 24. Now, just a word of caution, Pythagorean triples don't always work. Like, for example, if this was a 27, you can't divide anything out from 10 and 27, and there's no Pythagorean triple in that. So in a case like that, you would have to use the Pythagorean theorem, but I always like to look for triples, and when we see them, I definitely want to use them because it makes life easier. Okay, so that was step 2. Fill in everything you know, and we did come up with the height, and now we only have this one unknown here. So now in step 3, we're going to finish the problem, and in this case, we are actually solving because n is embedded there in the right-hand side. So here we go, guys. I'm going to leave this 1200 alone here on the left. I'm going to multiply a half times 24, and that's going to give me a 12, and then in parentheses, 60 plus n. Now, if we were in class right now, I would ask everybody, what do you guys think we should do next in order to solve for n? And every single person in the room would tell me to distribute the 12. And I promise you that will work. However, there's a faster way to do this. Guys, we're trying to isolate the n, this variable right here. So putting more stuff on top of the n, like multiplying the n by 12, just creates one more thing I'm going to have to undo before I'm done with this problem. The much better way to look at this problem is the following. Where's your variable? Right there. What's being done to it? Well, first they're adding 60 to n, and then they're multiplying that by 12. And how do we undo what's being done? Well, the last thing being done there was multiplication by 12, so the much faster thing to do is to get rid of that multiplication by 12 by dividing both sides by 12. Okay, this is going to allow me to get the problem done in 2 steps rather than 3 or 4. 1200 divided by 12 is just going to be 100. Those 12s cancel each other out, and we now have a 60 plus n. And all we need to do to get n by itself now is subtract 60 from both sides. Those cancel, and we should have our answer now of n equals 40. Wait a minute. I did give you units right here, square centimeters, so that means that every length here should have been measured in centimeters, and that's what we would come up with here for n. I never want you to trust your eyes, guys, but if this quantity from here to here was 50, this being 40, yeah, seems fairly realistic to me. Okay, so that's 2 examples of trapezoid problems. One here that's pretty straightforward, where they gave you everything you needed, plus some extra information right here, and asked you to find the area. But we're going to see a decent number of problems like this, where they give you the area, and they want you to solve for a missing side. But again, the 3-step method guides you through it. Write the formula, fill in what you know, and then either evaluate or solve. Okay, guys, 2 more formulas right here. The next one we have is for finding the area of a rhombus. And again, I think I read somewhere it's supposed to be rhombuses and not rhombi, because it's Greek and not Latin, but regardless, here we go. Formula for area of a rhombus is not that bad. 1/2 d1 d2. And remember, guys, with no symbols in between, that's implied to mean multiplication. So 1/2 times d1 times d2, and what the d's really stand for, guys, are the diagonals in a rhombus right here. So that would be diagonal 1, and this one right here would be diagonal number 2. So the diagonals are the 2 segments that go across the figure. One of them goes from A to C. We would need to know the length of that piece, and the other one goes from B to D. Now, if you care, and I doubt many of you do, and you can skip this part if you want, that formula comes from the idea that when you draw a rhombus and you draw the two diagonals in there, the diagonals are perpendicular and they bisect each other. This piece would be congruent to this piece, and this guy here is congruent to this guy. And what that means is that a rhombus can actually be cut up into 4 right triangles that are all congruent to each other. All right, so let's think about what we know then about the length of each one of these pieces. If we've said that AC is diagonal 1, then this piece right here from A to the center is going to be half of that diagonal, 1/2 D1. And that means that from B to the, I probably should have called this E. BE then would be half of diagonal 2. So let me draw a little arrow going right there. That would be 1/2 D2. So the area of that one yellow triangle we have, guys, remember that area of a triangle is 1/2 times its base times its height. And since we have a right angle here, I can say, okay, 1/2 D2 is going to be its base. And then the perpendicular piece right here, 1/2 D1, would be its height. So the area of that one triangle would be 1/2 times 1/2 times 1/2. That makes 1/8, and then the product of D1, D2. Now that would be the area just of that yellow triangle that we made right there. But the rhombus as a whole is made up of 4 of those triangles. So it would be 4 multiplied by 1/8 D1, D2, and the 4 and the 1/8 get multiplied together to make 4/8, which is 1/2 D1, D2. And that is where that formula comes from. Okay, so to find area of a rhombus, we need to know the lengths of both of our diagonals. So let's take a look at this rather poorly drawn figure that I made for you right here. It's definitely a quadrilateral, and I at least put the black tick marks in there to indicate that the 4 sides are all congruent. And as soon as you see a quadrilateral with 4 congruent sides, we know that it has to be a rhombus. Okay, so that tells me how to get started here. Let me switch back to purple. Step number 1, write out your formula. Area of a rhombus is equal to 1/2 D1, D2. And step 2, let's fill in what we know. Area then is going to be 1/2 times, well, we need to know the length of both diagonals. And right now I only see one of them, but luckily we know how long it is. This diagonal from here to here was given to us as having a length of 12 centimeters. But we need to know the length of D2, the other diagonal. And guys, it's a pretty simple concept. It's difficult to figure out how long something is if you can't even see it. So let's draw the second diagonal, the one that goes from here to here. And let's see, I don't like the way I drew that. And let's see if we can figure out how long, that was no better. That piece is right there. Well, like we talked about on the previous slide, every time you draw the diagonals of a rhombus, they are perpendicular to each other. So that's a right angle, and they bisect each other. So that original diagonal there that was 12 is going to get cut up into a 6 and a 6 right here. And now once again, I want to focus on one of these triangles. I'm going to highlight this one here in yellow, and I'm going to realize now, guys, that that is a right triangle, and we know the lengths of 2 sides in that figure. So I'm going to call this piece right here X, and we're going to figure out what X is. How could we do that? We could do the Pythagorean theorem, or we could look for a triple. Now, there's no triple with 6 and 10, but I notice again those are both even numbers, which means I could try dividing out a 2. 6 divided by 2 is 3. 10 divided by 2 is 5. Aha, this is a 3, 4, 5 Pythagorean triple, so we would multiply 2 times 4, and X would equal 8. So it's going to be very tempting at this point to be all proud of yourself and put an 8 right there, but whoa, 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 that's not quite right. This piece here is 8, and so is this piece right over here. So the entire second diagonal would be 8 and 8 put together. 16 centimeters then would be the length of this entire figure. Okay, so that's step 2, fill in everything you know. And now for step 3, let's just evaluate the right-hand side. You could do this, well, most of you would just grab your calculator and type in 1/2 times 12 times 16. If I were doing it by hand, I'd probably multiply 1/2 times 16 first to get 8, and then 8 times 12 is going to give you 96 centimeters times centimeters is square centimeters, and there's our answer to that problem. Of course, you also could have done half of 12, which would get you 6, and 6 times 16 is 96 as well. That's the good old commutative property of multiplication. Okay, so there's the one and only rhombus problem I was going to do with you guys. And let's take a look now at our final formula here. We're almost done with 11.1, area of a kite. And the formula, well, let's go back, guys. The definition of a kite is that it's going to be a quadrilateral, 4 sides, with 2 pairs of consecutive congruent sides. So you can see here with the tick marks that AB and AD are congruent to each other. And likewise, BC and DC are congruent as well. So that's what makes this figure a kite. And lucky for us, everybody, the formula for area of a kite, you'll notice, is identical to the formula we learned 2 slides ago for area of a rhombus. If we were going to prove it, it's not for the exact same reason. You do create 4 triangles here when you draw the diagonals in a kite. They're not all 4 congruent to each other. 1 and 2 are congruent, and then 3 and 4 are congruent, but I think I'm going to spare you guys me walking through where that formula comes from. Exact same formula here for area of a kite that we had for a rhombus. And once again, the D's stand for diagonals. AC is diagonal 1, BD is diagonal 2. Makes no difference which one you put where, since we're just multiplying these 2 numbers together. And one last problem here to wrap this up, but this is not an easy problem here, you guys. We've got some work to do on this, so let's get working on that. I think what I might do is maybe make this figure a little bit bigger. No, maybe I'm not going to do that. Okay, here we go. Let's group all that together, and then we can kind of enlarge this. Okay, so let's look at this figure here. Okay, I see the tick marks here up at the top and the bottom, so I know we're dealing with a kite. So step number 1, area of a kite is going to be 1/2 diagonal 1 times diagonal 2. Let's move on to our second step. Let's fill in what we know. Do we know the length of either one of the diagonals? And right now, the answer is no. I've got 15 and 41, which are 2 sides of the kite. I've got 12, which runs from here to here. But that doesn't tell me what I need right there in terms of either of the diagonals. So we've got work to do. Okay, one property, and if you don't remember, I'm hoping you can kind of tell from the diagram here, is that the diagonals of a kite are perpendicular to each other. We've got a right angle right there. And that means that there's a right triangle right here, and we know the lengths of 2 sides. So let's find the third, guys. Why don't we call this piece here an x, and let's try to find x, either by using the Pythagorean theorem or maybe by looking for a triple. 12 and 15 are both divisible by 3, and when I divide out that 3, I get a 4 here and a 5 here. This is a 3, 4, 5 triple. 3 times 3 means that x is 9. Now again, I think you can see the symmetry in this figure. This piece here is going to be 9 as well. So one of the diagonals here, guys, is going to have a length of 18, which is that 9 and 9 put together. Now, we still need to come up with the length of the second diagonal, and the 12 is definitely part of that, but we need to come up with the length of this piece over here, which I'm going to call y. And how are we going to do that? I'm going to go back to my highlighter, but switch colors. Right here, guys, we have another right triangle, okay? And we know the length now of 2 sides in that figure. 9 for a leg, 41 for a hypotenuse. And if you know your triples, sometimes life gets really, really easy. You could do the Pythagorean theorem here, but this is a straight up 9, 40, 41 Pythagorean triple, not being multiplied at all. So this missing piece right here is 40. And that means that the length of the second diagonal, the one that goes from here all the way down to the bottom, would be the sum of 12 and 40 added together. So we're going to get 52 for the length of that second diagonal. And now for step 3, I would just grab your calculator, multiply all that together. Ooh, can I do this in my head? Half of 18 would be 9. 9 times 52, 450, and another 18. I believe that's going to be 468. I didn't give you any units in this figure, so we're just going to put square units at the end there, and that's our answer for the area of the kite in this example. So as you guys can see, there's a large amount of trigonometry that still figures into coming up with missing sides or missing heights in this section right here. So everything that we've learned recently, guys, in trig, in terms of Pythagorean theorem and the Pythagorean triples and special right triangles, let me think, there was a 60 in here somewhere, wasn't there? Yeah, this problem right here, all that stuff is still going to come into play, and we're going to need to know that in order to do well with all of these new formulas. So speaking of which, you guys want to make sure that you've got, I believe, 5 formulas in your notes right here. One of them here, area of a parallelogram, is base times height. Another one, area of a triangle, is 1/2 times base times height. And then the 3 new ones we covered in this section. Area of a trapezoid, that's 1/2 times height times base 1 plus base 2. Area of a rhombus is 1/2 times diagonal 1 times diagonal 2, and then area of a kite is the same formula as area of a rhombus, 1/2 d1 d2. And once you get the formulas down, hopefully this section isn't going to be that bad. All right, guys, let's dive into that 11-1 homework. Good luck on all that. Let us know when you have some questions.